Each of exercises 51 through 53 refers to the Euler phi function denoted phi, which is defined as follows. For each integer n greater than or equal to 1, phi of n is the number of positive integers less than or equal to n that have no common factors with n except plus or minus 1. For example, phi of 10 is 4 because there are 4 positive integers less than or equal to 10 that have no common factors with 10 except plus or minus 1, namely 1, 3, 7, and 9. Prove that there are infinitely many integers n for which phi of n is a perfect square. Now, this is one of those instances where I think you actually have to look in the solutions section of the textbook because it says this hint right here. Use the result of exercise 52 with p equals 2. So they're not actually giving you the solution in the solution section here. They're giving you a hint, and I think you really need this hint. Without this hint, I don't see how you can really answer this question. Now let's take a look at number 52. It says that prove that if p is a prime number and n is an integer with n greater than or equal to 1, then phi of p to the n equals p to the n minus p to the n minus 1. Now, the reason why this is important is because there's a way of producing infinitely many integers, n, for which phi of n is a perfect square using this formula. But you have to pick a very specific prime number to make this work. And that prime number is p equals 2. If you notice, phi of 2 to the n, according to this formula, is 2 to the n minus 2 to the n minus 1. Now, this expression can be factored because both of these terms here have a common factor of 2 to the n minus 1. That's the greatest common factor. So we can factor that out here to get 2 minus 1. 2 minus 1 is just 1, and multiplying by 1 doesn't really do anything. So this is 2 to the n minus 1. So the 2 minus 1 is just 1, and so this simplifies to 2 to the n minus 1. Now, the question is, how is this relevant to the original question? How do we produce infinitely many integers n for which phi of n is a perfect square? Well, we can specifically choose odd integers for n. Let's imagine for a moment that n is odd here. If n is odd, then this exponent is even. And if this exponent is even, then this entire number will end up being a perfect square. And since there are many odd integers n, there are many numbers 2 to the n that we can use to produce phi of n as a perfect square. So let me explain a little bit further. Let's assume that n is odd. So let's assume that n equals 2k plus 1 for some integer k. That's the definition of an odd integer. In this specific case, if n is odd, then that means that this is really saying phi of 2 to the 2k plus 1 equals 2 to the 2k plus 1 minus 1, which is just 2 to the 2k. But I'm going to write this as 2 to the k squared. This result is a perfect square because this number inside the parentheses is an integer. 2 to the k is going to be an integer. So if we set n to 2 to the 2k plus 1 for some integer k, then that means that phi of n is a perfect square. And in particular, this is the equation to find what the output of phi of n is here. That's a perfect square because this whole thing is being squared. Now, how do you come up with the solution on your own other than, number one, having the hint from the solution? But also, I think that this is a very clever approach. I had to think about this one for quite a bit, but to be fair, this is number 53. Since there are infinitely many positive integers for k, then there are infinitely many outputs that are perfect squares. Thanks, everyone, and I'll see you in the next video.